Yes, am I audible, Basmi?
Yes, ma'am, you're audible.
All right. See, let us start with this assignment. Second question you were having a little trouble in, right? The first question was what we've already completed in the class itself, right? See, the second
Yes,
question
ma'am.
is exactly similar to that. It's just that since it is hollow, so the radius that we are getting, the radius is not just R or A, because you have
Mm.
the radius, because it's a concentric cylinder, right? See, it says a hollow cylindrical conductor of radii A and B carries a current I uniformly spread over its cross section. Okay. It says we have to prove that the magnetic field inside the body is given by this. So same method. See, if I just draw it, it would be something like this. The entire part, and which one is greater? Okay, it has not mentioned radii A and B. So A will be inner one, B will be outer one, because it is saying B square minus A square. It means definitely B is the greater one. So this will be, let's say, B. And let's say here we have a current. Here we have this, and whose radius is A. Okay. Now here if I take the radius is going to be B minus A. Correct? Now see, we are going to apply
Yes, ma'am.
concept that we studied earlier as well. Okay. What did we study? That we have to find out the value of I enclosed. This is the task, finding the value of I enclosed. Once you have the value of I enclosed, then the formula is solved, the question is solved, correct? So what we do,
Yes, ma'am.
see, for when we have taken an inside part, let's say we have taken a radius which is within this. Okay, let's say this is R. Okay, so we want to first, let's see, through this bigger one means current. I'm doing the same steps that I've done earlier. So current through area of pi b minus a whole square. The area will be b minus a whole square of this part. See, this is the portion, this one. This is the portion whose magnetic field we have to find out. Okay, this one. This is the portion. Okay, so what will be this
Yes,
area?
ma'am.
Minus a, correct? So current
Yes.
through b minus a whole square is given as I. So current through unit area will be I divided by pi b minus a whole square.
Yes, ma'am.
We have to find out through which? Through this one, the radius that we have fixed, this one, right? The radius that we
Mm.
have taken, the ampere circuital loop, this one we need to find out. So this will be current through, if you know unit area, so through unit area, you can find out through R minus A, right? You can
Yes,
find
ma'am.
out R minus A whole square. See, so this is one area. This is the area in which we want to find out the current. So total radiuses are correct, and the one that
Yes,
we
ma'am.
calculate is A. So when you are calculating this, it's going to be current through pi R minus A whole square is equal to, so see, this will be I by pi B minus A whole square into pi into R minus A square. Okay, means
Okay,
R
ma'am.
minus A whole square. So from here pi gets cancelled. Now see, you have the value of current enclosed now. This part is already there with you. Now, this is what? This is B dot dl's integral is mu naught I enclosed. dl integral of dl is 2 pi r. So here when you multiply 2 pi into r, this will be 2 pi r. B into 2 pi r is equal to mu naught I enclosed, which you've got. Same thing you will get. So it's just the same question, The thing is that here we do not have the radius as r only. The radius is in
Okay,
terms of
ma'am.
the concentric radius. Is this clear?
Yes, ma'am.
Okay, please note it down then.
Ma'am, in the question, it's given as r square minus a square, but in our answer, it's r minus a the whole square, right?
Yes, see, that can be solved if we take a very small length, let's say dr. Okay, if you take
Hmm.
this as dr, no, very, very thin section over here, this
Yes, ma'am.
dr, then you integrate that. Then you'll get, when you put the limits
Oh,
from a to r and r to a, that will come exactly the same because see, when you will have r, right, and when you integrate it, it will become r square, right? So
mm,
regardless
yes,
of
ma'am.
limits, it will be the same. Okay.
Oh, okay, ma'am. Ma'am, I'm done like.
Okay, this assignment you were able to do, right? This one was completed, right? Both the parts.
Yes,
So,
ma'am.
I hope All the three parts you have done by yourself, like you don't have any trouble with them?
No, ma'am. This was kind of easy.
All right. So now we'll have the class on Tuesday. Okay, not Monday. I'll not be able to take the class on Monday. So Tuesday we'll have the class. Tuesday, yeah, I'll tell you when can we have the next class. Okay. So we'll
Okay,
have
ma'am.
time because I'll try to complete this chapter right now. Today it will be completed. So please study this entire chapter, Basmi. Okay. So that in
Okay,
the next
ma'am.
class we are able to discuss the rest of the assignments also. We are able to discuss and take your doubts as well, and we can practice certain questions. Okay, because chapter 5th,
Okay,
6th,
ma'am.
7th, 8th, all these are very small chapters. So they won't
Mm.
consume much of your time. So it's okay, we'll complete those chapters so that before your exam we can have revision classes and we can prepare you for them. Okay. All right. See, torque on current carrying coil is important because the next topic that we have to do is completely based on this. So let us discuss this and then later on I'll discuss the numericals based on this. First, let me discuss what's the topic all about. So see, if I want to find out the net current, let's say here the current flowing is like this. Current is flowing like this. Now I find out the direction of the force. Let's say magnetic field is going inwards. So I'll keep my hand like this. See, the sheet isn't kept in the XY plane. Sorry, YZ plane.
Mm.
Okay. So when we have the thumb like this, okay, let's say, or in fact, let's assume the direction of magnetic field to pass through the coil, because usually it will pass through the coil, then only this coil thing will come in your alternating current chapter, but there's the concept is different. Now Basmi, here you have to do the right hand thumb rule along. Okay, you have
Ma'am.
the current flowing. How is the current flowing? See, look at this. This is how it is put. Okay, this is how it is put. Now see,
Yes, ma'am.
from this side the current is coming. This is put like this. Okay, this is your y axis, this is your x axis, z axis. Okay, y z axis like this. Now see, when it is put like this, current is coming like this out of the page towards me, right? This is how the value of the
Mm.
current is coming outwards.
Yes, ma'am.
So I'll keep my hand like this, right? Because in along the
Mm.
direction of current. So I'll keep my hand like this. But where is the magnetic field pointing? Towards the right, correct?
Mm.
So if
Yes,
I
ma'am.
turn my hand like this, now I can curl the fingers along magnetic field.
Yes, ma'am.
Thumb is pointing towards. Is that clear?
Okay. Yes, ma'am.
So tell me if this is, let's say, let me name this A, B, C, D. So across AD, the force is this, F1. You tell me the direction for the force across AB.
B.
Yeah, across AB.
Mm. Is it towards the left?
Not left. This is outwards. This AB side is outwards
Oh,
now, coming out.
yes, ma'am.
So force will be
Downward?
current
No.
is flowing like this downwards.
Mm.
Magnetic field is towards the right side. Curl the fingers towards the right. Where is the thumb pointing? Outwards.
Yeah.
This is coming outwards. F2. Tell me for BC.
Current is flowing this way. It's going downward.
Yes, it will go downwards. Look, the current is going like this and magnetic field is like this. So when we curl our fingers, thumb is pointing downwards. Yes. So this will be F3. CD.
Going inwards.
Inwards, yes, because the magnetic field, the current is upwards and magnetic field is towards the right. So when I curl, it is going inwards, right? So this will be inwards. Now, can you see, Basmi, all the forces are cancelling themselves?
Yes, ma'am.
Yeah. So look, B is the uniform magnetic field. L is the length of this coil. B is the breadth of the coil. Theta is the angle between the plane of the coil and the magnetic field. Means this. This is the plane of the coil and this is the magnetic field. This is theta. Like this. Okay. Let's say the coil, the magnetic field is like this. And the coil is placed like this. So this angle. Okay.
Mm.
And N is the number of turns, I is the current which is flowing. So you should remember that the net force will be F1 plus F2 plus F3 plus F4, which is equal to 0. So no translation motion. No translational motion. This means the coil will not be moving further. Like if you have the coil, this coil will not be going further, outwards or inwards or up, down, right, left, anywhere. This coil will not move. But there will be a torque is existing, and torque is a rotational force. So if the coil is not moving forwards or backwards, the coil can rotate at its position. Okay, because torque is existing.
Ma'am.
All right. So the formula of torque is very simple. If we have torque, one formula I'll tell you, it is P cross E, which we have done in electrostatics. So similar to it, you will have C. Dipole moment, magnetic dipole moment is M. So this will be M cross electric field. This will be B. So this is the formula for the torque. Okay. So torque is, this is
Ma'am.
one formula, magnetic moment cross magnetic field. Like this. The way you have this formula, exactly same. Now see, if your torque is equal to M cross B, magnetic moment, what was the formula we studied yesterday?
Mm. AI.
Yes, A into I. Number of turns are there. So NAI B sine theta. This will be the formula which usually is written as NAIB because most of the time your if means sine theta is equal to 1. That is theta is equal to 90 degree. Is that clear?
Yes, ma'am.
You copy this, then we'll see some more things. Okay? Please write.
Okay, ma'am. I'm done. Ma'am, I'm done. Ma'am, I'm done.
Okay, look, coming to conversion of galvanometer into ammeter and voltmeter. This is a very small, easy topic, and it is related to your practical portions also that must be done in the school. In the school, your first book is over, or was it going on?
I'm not sure. Yes, let's I didn't check it yet, ma'am. I'm not sure.
Tell me the chapters that are completed.
Yes, ma'am. 1 second. Electric charges and fields, electrostatic potential and capacitance, current electricity, moving charges, magnetism, alternating currents, and electromagnetic waves.
Okay, these are
We
done.
are still doing we're still doing induction, ma'am. We didn't finish induction.
The classes. Okay, just a minute.
Ma'am, please say something.
All right. Okay. So let us complete this. This will complete our chapter. Conversion of galvanometer into ammeter and voltmeter. Before that, you need to understand what is exactly a galvanometer. So see, in your circuit, whether the current is existing or not, means there is a presence of current or not. That is done with the help of a device known as a galvanometer. Basically, this is a device which is used to detect current. It won't tell you what's the value of current. Detect current means it will just tell you whether the current is present, yes, or it's not present. Okay, it will just tell you yes or no, whether the current is existing in your circuit or not. Because see, when you have connected the circuits and everything, when you have switched on the circuit, so you cannot see the current, right? And you're not able to see the bulb is glowing or not. You're seeing the bulb is not glowing. So it means, if is there a problem with the bulb, or is the current not flowing? Lots of things are there from where you require the detection of the current. So the detection of the current is done through a yes or a no. That device is known as a galvanometer. So we have a moving coil galvanometer, which is based on the concept of torque that we have studied. This torque we'll do again in the next chapter. That's why we didn't do it in detail, but a little bit of torque you should know when you are entering this chapter. So this is how this looks like. The actual picture of the galvanometer is, this is the whole scale, pointer scale. And this is the pointer. And here you connect the wire. You just wrap the wires here also and here also. You just wrap the wires like this. And this is how they are connected. If there is any loosening in these connections, then it won't be able to detect any. It just moves here or on this side. Okay, in either direction this moves. Okay. And either of them will tell you whether the current is present or not. Okay. That is what is a galvanometer all about. Then there's a principle of galvanometer. Before that, understand the inner structure of it. Like what is there within this. So within this, there is a scale. This is the scale where the readings are made, which you can see from outside like this. These readings, which you can see from outside. This is that scale which is inserted within. Then here you have the permanent magnets. Permanent magnet. These are radially curved, means the magnet is like this, and then this is radially curved like this. Then the south part is taken and the southern part, it is like this, it is radially curved like this, radial. So as to get radial magnetic. Okay, this is the curvature of the magnet. This is the curvature of the magnet, and these are the radial magnetic fields. The magnetic field is in the form of circle. That is what is meant by radial magnetic field lines. Okay. Now here there is a soft iron core. The circular part which you can see, this is a soft iron core. Soft iron core. Okay. Now on this there is a wrapping of wire, aluminum wire or any wire. These are wires wrapped. In basically, these wires are present just to wrap around it, wrap around the soft iron to produce the magnetic field. So wires wrapped on the soft iron core, which has a spring. This is a spring which is present. This part, there is a spring attached on which rests the pointer. This is the pointer. This is how it is constructed from inside. So what will happen when these magnetic fields are present? Because of these magnets and all these soft iron core and all the wrappings and everything, if there is current, what we have studied in the entire chapter, current leads to magnetic field. So if there is a current existing, in the system, it means magnetic field will be produced. Okay, let's
Yes,
say
ma'am.
current is existing in the system, in the wire in the system. So when current is existing in the system, magnetic field is produced. Now look, when the magnetic field is produced, it will allow this coil of iron core to rotate because of torque that we have studied. Yes, magnetic moment. We have seen no
Yes, ma'am.
net translation force is not there, but net rotational force is existing. So the coil which
Yes,
is
ma'am.
present, this will rotate, and as the coil will rotate, the wrapped wires which are wrapping the spring will allow the pointer to move. So that is what you see in the outer part, the detection of current, whether the galvanometer is showing you a yes or a no means, is it showing you that the current is existing or not. If
Yes,
let's say
ma'am.
there is no current in the circuit, then there won't be any rotation, there won't be any magnetic field produced, there won't be any rotation, right? And when there won't be any
Ma'am.
rotation, then the pointer will not move. So the pointer will just tell you whether the current is existing or not. Look, if it is staying at the 0 point, it means there is no circuit and there is no current in your circuit. If the pointer rotates, it will rotate on the degree of the rotation of the coil. Means if the torque is very large, the pointer will rotate more. So that will just tell you
Yes,
how much
ma'am.
current is present. But is the current 5 ampere, 4 ampere, 3 ampere? This won't be told through the galvanometer. It will just tell you current is existing on. Did you understand this part? What is the meaning of this galvanometer? How it works? I'll show you. See,
Yes,
this
ma'am.
part will be a little clear if I show you. See, this is exactly the same. What I have drawn here, this is the inner part. When you cut through the galvanometer, see, this is the scale which is observable. This is the scale which is just visible to us. Here, can you see the magnets are there?
Mm.
Look, these are the magnets. And look, they are curved radially so as to give the radial magnetic fields. Okay. This is the soft iron core over here, which is wrapped with the magnets, with the wires. See, lots of wires are wrapping. And here is a spring present, and which has this pointer attached. This thin line is the pointer, okay, which is resting on the rest of the things.
Ma'am.
So this is how the entire galvanometer works. Is this clear?
Yes, ma'am.
Now let me tell you what's the principle behind it. It says that if a current carrying coil means current is existing, conductor is there, coil is there, current is existing, is placed in a magnetic field which is constant, not a variable, because you have the radial magnetic fields which are constant, then it experiences current dependent torque. Means the torque is not due to any rotational force or something. The torque is coming because of the current existing, that tends to rotate it and produce angular deflection. This is the whole principle, and it comes to right as it is. Principle comes, this construction part comes. So in the NCRT, this diagram is drawn, so you can prefer this. This is just for your understanding it, how it actually looks like. So is that
Okay,
clear?
ma'am.
Did you understand?
Yes.
Okay, write down all these things. Then I'll discuss the numerical.
I'm done. Um, Done, ma'am.
Okay, so let's write the numerical part. See, this basically says that the principle says what? The principle says that if the current carrying coil is placed in a magnetic field where the magnetic field is constant, then it will experience a current dependent torque, okay, that tends to rotate and produce angular deflection. So here you will have a torque that is known as the deflecting torque. Means the torque that is deflecting the magnetic field, deflecting the coil. So the formula we have studied recently. Just tell me what's the formula?
AIB sin theta.
Yes, yes. NAIB. Correct. So torque deflecting will be NAIB. Now look, there will be a restoring torque acting upon. Okay, whenever you have the SHM or you have any angular deflection, there will be, see, if there isn't any restoring torque, then this pointer will always remain in this position, right? The pointer will continue to remain like this only. But if we have the restoring torque, then the pointer will come back to its mean position. So there is always a restoring torque that is acting. So this is the restoring torque. Now, if you remember in your class 11th, you must have done the formula F is equal to Kx for the displacement. Remember that force is directly proportional to displacement in the case of SHM.
Yes, ma'am.
So if this is something related to rotation, this becomes tau is equal to K theta. Means for linear displacement, you have angular displacement. For the linear force, you have the torque like this. Where your K is the spring factor. K is nothing but the spring factor. Spring factor means it's a constant for various system. Like for the spring mass system, if you have the spring mass system attached, then this K is called as the spring constant. Remember, you must have done spring constant. Or if it is a pendulum system, then the value of this K becomes 2 pi. So many things are there that was from your class 11. So the restoring torque will be equal to K times theta, where K is the spring factor and theta is the angular deflection. So if the torque has deflected, same amount of torque will be required to bring it back, right? If it is deflecting to some amount, the same amount of torque will be required to bring it back. So we can say the torque deflecting is equal to the torque restoring. So I can say NAIB is equal to K theta. From here, the value of deflection, this theta, this will be NAIB divided by K. Theta is the angular deflection. N is the number of turns. A is the area of the coil. I is the current. B is the magnetic field. And K is the spring constant. Is this clear?
Yes, ma'am.
Okay. So this is what is theta. Now, see, there is a term sensitivity of a galvanometer. See, usually we often use this term sensitive, right? Sensitive we use for people also. The person is sensitive. So what does this mean? That for a very small stimulus, the person is giving a reaction which is more than required, right? That is what we said. That is what is
Yes,
meant
ma'am.
by sensitivity, that you are able to understand more than what is required. So galvanometer, when is a galvanometer sensitive? It is that even for a small amount of current, it shows large deflections. Okay. If it is able, even it is able to detect small values of current. And for these small values of current, it is giving you larger deflections. So it means it is very sensitive. Even a small amount of current is giving huge deflections. Got this meaning of sensitivity?
Yes, ma'am.
Okay. Now there are two kinds of sensitivities, the current sensitivity and the voltage sensitivity. Current sensitivity basically means the whatever is this theta was the angular deflection, that is the deflection. So this means current sensitivity means theta divided by current. The deflection per unit current is the formula for current sensitivity. Meaning, I hope it's clear. Meaning is for a small value, it is giving you deflections, which could be neglected, or a very small movement in the pointer could have been shown. But no, it is giving you big deflections. So theta is what? NAIB divided by K into this I. The current will get cancelled. What is current sensitivity? The formula for current sensitivity is NAB by K. Got it?
Ma'am.
This is the current sensitivity. Then comes the voltage. So voltage sensitivity means the same thing that you're getting. See, this sensitivity is for this angular deflection. So when I say deflection, deflection is referring to this theta only. Okay. So this is angular deflection only, what we have studied here, per unit voltage. Okay. Now look, theta is what? NA IB divided by K, while voltage from Ohm's law is equal to I into R. I again get cancelled. Voltage sensitivity's formula is NAB divided by K to R. You can understand through this also. I is this, so I by R will be basically voltage sensitivity will be current sensitivity by the resistance, where your R is the value of the resistance. This is resistance. Is this clear till here?
Yes, ma'am.
So this is voltage sensitivity. Okay. Just let me write.
Yes.
This is the resistance. Okay. Is that clear till here? It's clear? Okay, write it, Basmi, from this side.
Ma'am, I'm done. Done, ma'am.
Okay, let's move to the conversion of the galvanometer into ammeter. So let's say you don't have the ammeter. Ammeter is a device that measures the value of current. Okay, what exactly is the value of the current? So if you don't have the device ammeter, it looks just like the galvanometer only. Then what you can do, if you have galvanometer and you have a resistance which can be connected in parallel to the galvanometer and the value is less. Means see, I'll show you. This is the galvanometer with its resistance, let's say G. Okay.
Ma'am.
Now, if I connect a resistor in parallel to this, which I am calling as the shunt. Shunt is just so that the current can just bypass it. Okay. So this is the shunt, this is the galvanometer. Now, conditions for this shunt is that it should be connected in parallel and the value should be less. So look, when the current comes, let's say I amount of current comes. Some amount of current will go here, Ig. So how much will go through this shunt?
I minus Ig.
Yes, I minus Ig. I minus Ig is passing through here. Now see, voltage across this part. If I say the voltage across here and the voltage across this, won't they be the same? Let's say this is V.
Yes, ma'am.
Voltages will be same. Why?
Because voltage does not split, right?
What?
Current, current splits, voltage does not split. Actually, there is shunt resistance, so there will be a
Your
difference in
voice
voltage.
is
Yes.
cracking. Can you just speak a little louder, Basmi?
Ma'am, can you hear me now?
Yeah, say.
Ma'am, voltage does not split between two wires.
That is in parallel connection. Because it's parallel connection. In parallel connection, voltage does not split because it remains constant. Yes.
Yes, ma'am.
So what's the voltage across the shunt?
Uh, V itself. Across
What is
shunt,
the
it
value
will
of this V?
split.
Huh?
Ma'am, what's the
What?
value of V?
Yes, Basmi?
Oh, okay. I R like that. I minus I T into S.
Yes.
I
You have
minus
to use
I T
the.
into S.
And what's the voltage here?
Ma'am, can you repeat your question?
What's the voltage here?
V.
Which is equal to
V,
what?
right?
V is the voltage that we are assuming. What's the
I
value of this V?
minus I minus I T into S.
This is for this one. I'm asking for here.
I G V
Yes,
itself.
yes.
There's
Ig into
no
G.
difference.
Ig into G simply. G is the
Oh,
resistance. Ig is the current. Current into resistance. You forgetting
okay,
the
ma'am.
Ohm's law? Or you are not able
No,
to
ma'am.
apply? I
I
hope you
thought
remember.
that
No.
G
Yeah,
is
this is
not a
G is the
resistance.
resistance. G is the resistance. Like S is the resistance, no? G is the resistance. Okay.
Okay,
See,
ma'am.
potential difference across galvanometer will be equal to potential difference across shunt. Across galvanometer, it is G into Ig. Okay, and this is exactly what you said. I minus Ig into S. Now from here, I can get the value of shunt as Ig into G divided by I minus Ig. This is the value of the shunt resistance. Now is this clear?
Yes, ma'am.
Now see, if I get the value of shunt resistance and I want to find out what's the value of this main current, I can calculate. So without having the galvanometer, I am able to get the value of the current. Got it?
Yes, ma'am.
Okay, write it, then we'll see how to convert it into voltmeter.
Okay, ma'am. None, ma'am. I'm done, ma'am.
Okay, look now the conversion of galvanometer into voltmeter. So for voltmeter, you connect a resistor, like this is your galvanometer with resistance G, and you connect in series with a high resistance. This is not a shunt because nothing has been bypassed, right? The current is just going, so we just call it the high resistance. Okay, this is the resistance whose value is high. So just opposite, series and high, there it was parallel and low. Got it? Now, here the amount
Yes,
of
ma'am.
current that is flowing is IG. Now you tell me, you apply and tell me what will be the voltage.
Voltage will split. Okay, it's IG into GR
Yes. Into
G
G. So what about R? Think
G plus
till yes, G plus R. Very good. They're in series, Basmi, no? See, the
R.
R
Yes, ma'am.
equivalent will be here R plus G. And using your Ohm's law, this is nothing, but we are just applying the Ohm's law. Correct? So V is equal to Ig into G plus R. From there, see, if I write the value of G plus R, I'll get V divided by Ig, and value of
Yes,
this
ma'am.
resistor will then be V by Ig minus G. Okay, this is the value how you can calculate the resistor. Got it?
Okay. Yes, ma'am.
Write it.
Done, ma'am. Done, ma'am.
Is it done, Basmi?
Yes, ma'am.
Oh. Let's look at a numerical. It says an ammeter of resistance 0.8 ohm can measure current up to 1 ampere. Okay. It says what must be the shunt resistance to enable the ammeter to measure current up to 5 ampere. So here, what is your ammeter? Basically, it's the galvanometer, right? Because that's how we have converted it. So capital G is 0.8 ohm while the current through the galvanometer is 1 ampere. It is saying current when shunt is connected. So the value of the current is I is 5 ampere. It is saying what is the value of S. Got it? Just understand the meaning because now solving part I know you will be able to do. You just have to relate that what is the meaning of it. Okay. An
Okay,
ammeter can
ma'am.
measure means an ammeter can measure, but we don't have the ammeter. We have the galvanometer. So for us, this will be the data. So you write all the data, then you write the value of the shunt as Ig into G divided by Ig. What was it? I minus Ig. I minus I. So this is 1 into 0.8 divided by 5 minus 1. So 0.8 divided by 4, which is 0.2 ohm. Yes?
Yes, ma'am.
Okay. Coming to second part, what is the combined resistance of ammeter and shunt? Means now ammeter is this shunt and the resistance of the galvanometer, they are combined. So they're saying what's the combined value of their resistance? So it's very easy. Galvanometer's resistance is 0.8 ohm. This is our ammeter, no? Galvanometer is technically acting as our ammeter. And value of the shunt is 0.2 ohm. So what's their combined value? V plus S is zero point 0.8 plus 0.2, which is 1. Yes.
Yes, ma'am.
Okay. So combined resistance. Now see, the galvanometer and this. No, okay, wait, no, they are connected in parallel. Shunt, it's not the resistor. We cannot add them, no. The shunt and the galvanometer, they are connected in parallel. If this was the resistor, we would have added. But see, the galvanometer is there, G, and the shunt is there, S. So they are connected in parallel. So for the shunt, the combined resistance means what's the equivalent? So 1 by R equivalent will be 1 by G plus 1 by S. If it was the resistor for the voltmeter, if it was not ammeter, if it was voltmeter, then we would have added. You're getting my point?
Mm.
R equivalent will
Yes,
be
ma'am.
E into S by E plus 0.8 into 0.2 by 0.8 plus 0.2. This is 0.16, right?
Yes, ma'am.
Okay, please write this down.